All right. Good morning, good evening, good afternoon. Welcome to this presentation on designing grid interactive smart communities using CityLearn. My name is Altan Ege. I'm a faculty at the University of Texas at Austin, and I'm excited to be here. Thank you for the organizers for inviting me. Thank you for the opportunity to speak remotely. Unfortunately, I can't be there in person. Hopefully, this will be just as good and you can enjoy the work that we have done and how it relates to advanced data analytics for energy management. I have about a three-part presentation. The first part is a bit of a motivation and background work, and I have a center big part showing you some results of some of our recent work on how we manage battery control in a residential neighborhood in multiple buildings, and how reinforcement learning can provide better control than time of use, simple controls. And at the end, I'll kind of like summarize the learnings, and I'll give an outlook on where this is going. So some motivation, of course, I'm preaching to the choir. Buildings use a lot of energy. Buildings are responsible for a large part of greenhouse gas emissions, mainly because we like to be in buildings and like to be comfortable. So we need to heat and cool and provide ventilation, and that requires energy. We know what we have to do to reduce emissions from buildings, which is electrifying the grid and moving everything to electric. But what the problem with that will be is that when we electrify the grid, or when we decarbonize the grid and we provide mainly solar on the grid, we create what's known as a duck curve. We have an extensive load during the day, or reduced load during the day, and then a high ramping in the afternoon. And this is typically met with either gas or coal plants, and that's kind of like what we're trying to avoid. And more generally, what we try to do is to get away from this one-sided grid building notion that energy is produced somewhere and then used at the same time, almost in a different location. We want to be able to be more flexible with our energy use. And so when we can use it and when we can generate it should not necessarily be at the same time. So we need energy flexibility. And so this notion of flexibility, is like a red line through this presentation. So energy flexibility, very quickly, how we get there. The first one is not a flexibility yet. We have, but efficiency. Efficiency is when we keep the way we use energy, the time we use energy, but we make it a little more, we use less energy at the same time. So the original shape of the curve, the energy demand stays the same, and we just move it down. This is great, but it is not exactly what we want. This has been the way buildings have been made more efficient over the years, but it is not sufficient moving forward. The second part, like I said, is we can also generate on the buildings themselves directly solar. Sometimes this helps if your loads during the day line up with your demand with your generation. This is good, but again, especially in residential neighborhoods or residential buildings, your loads are not necessarily at peak during the day, but closer to the early or evening when your solar is gone. And so this is not that useful at that point anymore. So then the third option, and this is what we're looking for, is a more constant load profile, and more generic in some sense, so we can switch use on and off throughout the day the way we want, and be a lot more flexible. So load shifting, load shedding, and so on. So the question is, how do we get here into what you could call smart buildings, because they can, interact with the grid and so on at the time when it's needed. And so my work has been a lot on combining these two, so storage and control. Obviously, because if you do have storage, you can use it as a buffer, and short-term storage in buildings. So that's 2, 4, 6, 8 hours, something like that, not 2 weeks. And at the same time, when you have control, then you can make decisions under what circumstances, what optimality conditions or whatnot, you want to store that energy and you want to release that energy. So there's different ways to do energy storage. There's electric batteries, or more recently EVs in V2G or V2H applications. But all the forms also exist, like domestic hot water, water generator or water heaters, which also can be used as a form of storage and a form of demand response. And also just simple thermal storage in terms of shifting thermostats, to preheat and pre-cool buildings, and using the energy in the heat capacity of the building to store that energy and then release it later. Some of this is more or less controllable. This talk will focus on electric batteries because they're more directly controllable and allow for more fine-tuned response. But we have done work with domestic hot water as well, and hot water storage tanks and things like that. So when you talk about control, there is basically three big categories that control falls on. One is what we call rule-based control, which is a simple rules. So if then else decisions, if something happens, then you do this. This is what similar, I mean, not similar, this is sequence of operation in larger buildings. It's very simple in residential homes, if at all existent, but this is the baseline. Of course, this is very simple to set up. It's very easy to use, but it's harder to make optimal when you want to get really everything out of your system. So optimality is a challenge. Also, when things change in your homes, you need to go in and update these rules to make sure things are still good for your place. When you talk about something more optimal, closer to optimality, the next best choice is model predictive control. The idea here is that you know what you're controlling, so you know your systems, you have a model of your systems typically, whether it's a data-driven model or whether it's a mathematical and physical model. Typically, you would get a forecast X hours in advance, a time horizon, 24 hours, and you would make a decision, a trajectory for your optimal control in the future. So for every future hour, you would have an optimal control problem that you solve, and what you should do so that you have optimal decisions. And at every hour, you compute that. So as you move forward, you update your forecast, you update your decisions, you update your potential actions in the future. This works very well. This has the advantage that it's optimal. You can prove that things are optimal. The disadvantage is that you do need that model. And the other disadvantage is that you need to create that optimization at every single decision hour point that you're making. So it's quite computationally burdened at the execution time. And the last control method that has gained traction over the last few years, reinforcement learning. It's also a big class of algorithms, so I'm going to lump them all in one sense. The idea here is that it's very similar to model predictive control in that you wanting to go towards, what is the optimal decision, but instead of having a model of the system and computing at every time step, you create an interaction between your system and your optimizer, or your system and the agent, as we call it. And you try to understand how the system reacts to certain decisions. And it is through this interaction that you can derive the optimal control out. And technically, this can happen without a model, which is the main idea behind this. You don't have to generate the model. If you do have a model, you can also optimize in that model and create that interaction in the model. And then you can put it on the live system later on to finish the optimization. In the way you drive it is you provide rewards for the actions that the system takes. So it's very much what you would think of it from psychology. When you think of reinforcement learning, you present the system with a certain decision it needs to make. It takes a decision, and then you evaluate the decision and you provide it a reward or a punishment. And so that reward is then associated with the state and the action that it took. And then it will, remember that next time that the system that took it, and then, hopefully over time it will converge to a good solution. You can show for certain cases, for smaller problems with well-defined characteristics, that you can converge to optimality. For larger problems with large state space, this is a little bit trickier. So we don't really know if it truly reached an optimum or we're just close to an optimum at some point. In simple terms, reinforcement learning formalizes trial and error approach, but that just does not sound that cool. And so you do something, you find out what happened, and you improve your solution, and you keep going, right? And so the disadvantage here is that really it could take a long time until you find a good solution, until you converge to some of a solution. And if you do want to get to an optimal solution quickly, you do need that model in the beginning and optimize in the beginning. So in some sense, during execution time, you don't have a lot of computing to do because all you do is a few little updates. In that sense, it's a lot more efficient compared to model predictive control. But at the same time, you need to do a long, potentially you have to wait a little bit longer because you need to collect all that data, as opposed to MPCs where you have a model, which you need to generate somehow, which also requires data. So there's no clear solution here, or there's no clear trade-off in my mind yet, which one is better in what sense. It depends a little bit on where you want to spend your resources, really. My work has been a lot in reinforcement learning, so I'm going to make a case for reinforcement learning here because that's more awesome. Okay, so this is sort of like the backbone for that. If you're interested, we just recently published with really some amazing people on this list, including Alfonso as the organizer of this workshop. So if you're interested where the field is right now in terms of building energy management, using RL, I recommend this paper, what that summarizes, state of the art, a little bit of history, and also where the field is going. What are the research, the recent open, the open research questions. So a little bit back to our work. So what we've been doing over the past 5-6 years, developing CityLearn as an environment to study grid interactive buildings in a set. So many buildings, aggregate their response. We can control them individually or as a group. And really, we focused a lot on providing this to the community to be able to benchmark problems, to be able to use the same environment so that something, we can learn from each other and not everybody's starting the same sort of development. We did some sacrifices along the way, so to speak. So we have simple building models, we have simple system models. It's not a, Modelica Energy Plus detail. But at the same time, everything is in a single Python library and it interfaces with GEM so that you can really focus on the controls rather than getting lost in creating some complicated co-simulation environments that at the end of the day may not even be required for the control problem that we're looking at. It's open source, you can extend it. We also have the CityLearn challenge that just launched if you want to test yourself against a whole bunch of people good at this thing. Again, you can also adapt it to your own needs, and I'll talk about that a little bit later. Okay, so what did we do? To come back to the theme of the workshop, we asked ourselves, can we address one of the issues that I mentioned before, is that reinforcement learning needs a lot of data. And so 2 ways to address that is that you can jumpstart it with a known controller, which in our building case often can be a simple rule-based control that we have. So you don't start from scratch, really. You start with a known RBC, and then you improve that. And then the other thing that has been going around lately in our community is the idea of transfer learning. And Alfonso did a lot of nice work on that as well. And so the idea that we have one agent that we already have learned stuff on one building, can we just take it and move it to another building? And will that be as good as if we had just started on that building? And at the same time, the actual goal is, can we learn to flex our energy demand? So can we learn to shift loads in the buildings? And so the short answer to all of this is yes. The longer answer is in this paper, and the medium-long answer will be in the next sort of 2-3 minutes. I'll try to go through. So in this paper, we took real building data from smart meter data from a community in California, about 18 buildings. Smart meter data, solar generation data, the buildings were very efficient. They had also batteries. And so it was pretty much the problem that we were explaining. And so we added data to it. So what's the weather? What's the grid emission? What's the cost of the electricity? What the rate were, and so on. We created the virtual replica of this environment. Some would call it the digital twin. And then we did a bunch of control experiments to do this. Well, how much can we learn on one building and then pass it on to the other building? How good is it really compared to if you just run one building? How good is the RBC, the rule-based control, which we used for the initiated using the time of use control? So charge when it's cheap, charge your battery when it's cheap, and discharge your battery when it's more expensive during peak hours. So those are questions that we followed, and I'll give you a brief sort of like overview of what came out of that. So here's a community in Fontana, California, in I believe Southern California. So it's very sunny. The control task was to charge and discharge the battery in each of these homes. This was instrumented by EPRI, the Electric Power Research Institute, a few years ago. They did their own study with simple RBC control of the batteries, and trying to understand the value of the batteries in this community. And so the data was available. We couldn't do any more control, unfortunately, but we could create the exact virtual replica of the homes and run the study through them. So here are some results, and there is a lot of numbers and a lot of colors, but I want you to focus on the three colors maybe. So the orange bars represents what we would call perfect knowledge. So you optimize each building individually using the RL controller, and it's basically learning everything. You have the full year of the data, and then you execute on the same year. And so it's really just like the best of the best you can get with the approach that we use. So that's, you can see here, one, the reference is the baseline, so no battery energy use, and this is sort of like some KPIs that I'll show you. For example, the annual electricity demand using this controller went down by 15% compared to if you have no control and no baseline, so that's great. And electricity cost down by 20%, which is also great. The blue bar here is transfer learning. So this is, you learn for, I think we used 2 or 3 months on one building, and then we applied the known, so that learn agent on all the other buildings. And we did it with every building. Then the details are in the paper, and this is the average result. So essentially, if you learn on a wrong building, in this case, you can still get 10% electricity demand reduction. So it's a little worse than if you know everything, obviously, as expected, but it's not as bad as if you were to use a time of use tariff, which is 5% increase compared to the no control baseline. So there really is value in using these smart controls, and you can actually get a lot done. And what this really means is that the current setups are so bad that there's not really optimized for individual building demand and occupant behavior. So both electricity demand, electricity costs go significantly down. The time of use tariff control for batteries does not give any advantage, and this is what a lot of the studies have found. And then they conclude that batteries have no advantage economically because there's very little that you can win. But reality is that the controller is the problem, because with good control, you can, pull out quite a bit more on the cost. So a few more KPIs that we looked at, emissions and costs are very related. That's probably by design. Zero net energy on an hourly basis is very, very tough, or I think this is a monthly basis, so it's very, very tough to achieve still. The average daily peak, by far better with advanced controls. The ramping, so how quickly your electricity demand goes up after the sun is gone, again, much, much better using the advanced controls as opposed to time of use tariff and RBC. And the reason, if you start digging a little bit deeper into that, is because so the time of use tariff works as expected, and it shifts the load at times when you need it, when you don't have the demand, but everybody's doing the same thing. So everybody will shift the loads at the same time. And so essentially you're shifting your afternoon peak to your noon peak, which you may or may not be useful, right? But there's no control between that. In contrast, the RL controllers, and this could happen with MPC as well, or any other more advanced controller, they adapt to the individual building's profile. And so because these are individual homes with individual profiles, you get individual sort of like optimized load shape profiles and load shape control, which then aggregated provides a much more smoother profile on the neighborhood level. And you can see that when you aggregate all the buildings together, the no control profile here, the black one, which is the reference, and then the RBC, the time of use controller, creates this peak in the middle, where before there was none, because this was during the day and the demand goes down because they were using the solar. But now we have increased it because we want to charge our batteries while we're using the solar, so the demand to the grid increases. In the evening, there is no demand because that's what batteries are being discharged, but everybody's doing the same thing at the same time. And so the overall peak of this neighborhood actually increased, the aggregated peak. And this is one of the key messages, is if we do not control appropriately, we will not end up with a good solution, and we will end up with peaks at times when we don't want it. Similar things have been observed with doing smart thermostat control, and everybody's preheating their homes at the exact same time, and the whole neighborhood's load goes up like crazy because all the smart thermostats are programmed in this exact same way. So there is a lot of work to be done on coordinating these signals appropriately, so that we don't end up doing this. In contrast, the RL controller, again, there is no information exchange between these. This is just because each of the controllers is, optimizing their own behavior. But the end result, by chance almost, maybe, or maybe not, is that you have a much smoother behavior and compared to both of them. Like it's a lot higher load here, but a lot lower here. So it's an average much, much smoother than what you had before. The ramping is a lot smaller if you compare the slopes of these curves. And so you're a lot closer to this blue curve, which is where we started and we want to go, which is like a very smooth load shedding, load shifting as we need for our environments. So this was, like in the spring when we published this. In the meantime, over the past year, with a big group composed of Alfonso's group and Mohamed Ouf in Montreal and LBNL, Han Li and Tian Sen helped us put together a big upgrade for CityLearn. So right now we can work with the end-use load profile database and the RESTOC database for the US. So we can have very typical neighborhoods that we can generate these sort of problems and these sort of analyses for grid interactive buildings, and do all kinds of load shifting and load shedding, thermal storage, electric storage. We are adding EVs in the next couple of weeks with a group in Portugal. We're also working with some folks in Belgium to provide grid models or generation models so that we have the supply and the generation side at once, in which case you have really a full picture of what's happening in your electricity system, which will help really to move this problem forward. And at the same time, it's agnostic to how you control it, right? So that's the beauty of this. You can use the RL, you can go MPC. Some folks have compared MPC and RL using CityLearn, and solar and battery is very cool. So that's exactly why we do it. If you want to hear more about this paper in virtual session 2.3, we have the more details about this. And we also have a workshop at BS23, workshop 8, when Kingsley will walk you through this example or slightly different example, and just get you going and get you started so that you can explore it for yourself and see how awesome it is, basically. So that's it. Thank you for listening. Hopefully it was entertaining enough to watch it on video. Please get in touch if you have questions, if you're interested in working with us, if you're interested in testing stuff out, interested in modules, adding, get in touch. Check out the workshop, which should be workshop 8. I forgot the date and the time, but it should be available. It is virtual, so hopefully many people can attend. And yeah, I look forward to hearing from you. Thank you very much.